Hey everyone, my name is Sahil, and in today's video, we will understand the basics of designing an ESE lighting protection system. But why should you listen to me? At Axis, we've been manufacturing a wide range of earthing and lighting protection systems for the past 30 years. This includes lightning arresters, earth rods, ESEs, and everything else you can think of. You'll see our products installed in solar farms, data centers, commercial and residential projects in more than 100 countries around the world. Let's start with asking the very simple question, what is an ESE lightning arrestor? Also known as an Early Streamer Emission lightning arrestor, this technology offers safety from direct lightning strikes. The aim of this device is quite simple. It increases the radius of protection compared to a conventional lightning arrestor. It does this by sending the upward streamer from the ESE towards the downward streamer from the cloud, up to 60 microseconds earlier than a conventional system. By doing so, it reduces the number of lightning arresters and down conductors you will need for your structure. Yet, it provides complete lightning protection. It protects by ensuring that lightning strikes are safely channeled instead of striking random objects. The lightning current is directed through the ESE lightning arrestor into the ground. We have a detailed video explaining the working principle of the ESE. The link to that video is in the description. But there is something very important. Installing an ESE lightning arrestor alone does not guarantee protection. The performance of the system depends entirely on how well it is designed. If the design is inadequate, the radius of protection may be wrongly calculated, critical areas of the structure may remain exposed, or the earthing system may not be able to dissipate the lightning current effectively. As a result, before installation, you must understand the basic design steps involved. And now let's go step by step and understand how an ESE lightning protection system should be designed properly. The first step is risk assessment. In this step, you check how exposed your structure is to lightning and what will happen if it gets struck. You start by looking at the location of your building. Then you check the dimensions of your structure, the number of people that are there in the structure, the duration they are present in the structure, and the usage of the structure. If your site is in a region with high lightning density, your probability of being struck is naturally higher. Areas with frequent thunderstorms demand a higher level of protection compared to areas with lower lightning activity. Next, you evaluate the physical characteristics of your structure. If your building is tall, isolated, or located on elevated ground, it is more likely to initiate an upward leader and attract lightning. An upward leader is a rising spark from the structure that connects with the lightning coming down from the cloud. Then you must consider how the structure is used. If your facility is a hospital, data center, telecom site, industrial plant, or fuel storage area, the consequences of a lightning strike are severe. In such cases, you cannot accept even moderate risk. Your protection level must be high. Based on all these factors, you determine your required protection level. That is level 1, level 2, 3, or 4. Level 1 gives you the highest degree of protection, while level 4 provides a lower but still controlled level. This decision is critical. If you underestimate the risk, your system may fail during an actual lightning event. If you overestimate it, you may spend more money than is necessary. Therefore, risk assessment is a mandatory first step. The second step is the selection of the correct ESE lightning arrestor. After you complete the risk assessment and decide the protection level, you select the ESE lightning arrestor based on the calculation. According to NFC 17102, the protection radius of an ESE depends on 3 things: the installation height, the selected protection level, and its early streamer emission time, which is delta T. The protection radius is the horizontal distance around the arrestor that remains protected. If you install the arrestor higher, the radius increases. If you choose a higher protection level, the radius becomes more conservative. However, it provides an umbrella protection. Delta T represents how much earlier the device emits the upward leader compared to a conventional lightning arrestor. It is measured in microseconds. For design as per NFC, delta T can be between 10 and 60 microseconds. You calculate the protection radius using this formula. Then you check if that radius fully covers your structure. If the calculated radius does not cover the entire building, you cannot assume protection. You must either increase the height or add another arrestor. So, selection is not about choosing a model at random. You calculate, verify the coverage, and then finalize the device. We have a detailed video that explains the coverage area calculation. The link to that video is in the description. Now, step 3 is the placement of the ESE lightning arrestor. You must place the arrestor at the highest point of the structure. This gives you the largest protection radius for a given height and protection level. Next, you must match the placement to the shape of the structure. A long roof, multiple levels, or several blocks can leave corners and edges outside the covered zone. So you place the arrestor where the calculated protection radius covers a full structure. Then check the surrounding area. If you have a nearby object that sits higher, like a tower, mast, or another building, lightning will prefer that point. After placing the ESE, you keep a clear and direct path for the down conductors to reach the grounding system. If you're finding this video helpful, please subscribe to us for more insightful videos on electrical engineering. Now, step 4. Design of the down conductors. You design the down conductors because the lightning current must travel from the ESE to the ground through a safe path. In an ESE system, you connect each air terminal to at least 2 down conductors. You use 2 so the lightning current divides and reduces stress on a single path. You must install them at opposite sides of the structure, as this spreads the current flow and reduces the chance of side flashing on one side. You must keep distance from other metal paths and internal cables. Lightning can jump to nearby conductive paths if they sit too close. Your aim is simple: giving lightning a direct path to the earth so it does not travel through your structure at all. Now, step 5. The design of the earthing system. Lightning current must enter the soil in a controlled way. If the current cannot disperse into the ground, it will be a threat for your structure and your equipment. You connect each down conductor to an earth electrode system. This gives the lightning current a direct path into the soil. Ensure the earth electrodes are properly interconnected. This keeps your system at the same potential during a strike and reduces the risk of side flashing. The required earthquake resistance must be less than or equal to 10 ohms. I hope you now have a clear idea of how a ESE lightning protection system must be designed. Please note these calculations and design should only be carried out by a competent or authorized engineer. At Axis, we have a team of more than 50 engineers who are here to help you design, install, and test your lightning protection systems. Our products have been used in substations, data centers, factories, and even in everyday residential and commercial buildings. Before skipping to any other video, please note that these technicalities are different for conventional lightning arresters and ESE arresters. But how are ESE arresters different from conventional ones? You can understand this by watching this video right here.